Hello, Chemistry 12, and this is Mr. Chan. And what I'd like to do today is talk about buffer systems. Now, some of you have already been exposed to buffers in biology, but what I wanted to do was focus on how do buffers work? What is the chemical principles in how buffer system works? So what are buffers? So buffers is basically an equilibrium solution that tend to show little change when a small amount of acid or base are added to the solution. All right, the couple of keywords there is that they show little change when a small amount of acid or base are added to a solution. Now, there's two different ways to form a buffer. You take a weak acid and its conjugate base in the form of one of the salts, or a weak base and its conjugate acid. Now, this is key in terms of how you form a buffer. Okay. Now, let me give you an example here. So let's say we have hydrofluoric acid, so HF. And what we have is, let's say, sodium fluoride. Now, what you will notice is that sodium fluoride is the conjugate base of hydrofluoric acid. So these two are conjugate pairs, and this combination would be your buffer. So you would have your buffer combination. So how would it look? So you would have something like a big tub of hydrofluoric acid, and what you pour in, the salt, is you would have sodium fluoride. Okay, so what you have in this case, this is how you would form a buffer. Now, why should you have something weak and its conjugate pair? And the reason being is because by having this particular combination, you get a Le Chatelier shift, which helps maintain the levels of H3O plus or OH minus 1 in the solution. Now, let's say, for example, acetic acid and sodium acetate. Now, when we put acetic acid, which is a weak acid, when you look at your acid-base chart, when we put it in water, okay, because it is a weak acid, when we react it with water, it's in equilibrium. We have CH3, COO minus 1, and H3O plus. Now, because it is a weak acid, it doesn't dissociate completely. And remember, you use your Ka and ice tables and that sort of stuff to calculate the concentrations. You will know that the acid will be a high concentration and the products will be low. Okay. Now, this goes back to when we did our Ka introductions. We talked about, if we look here, let me see, keep on going down. Remember, you have an unknown concentration, and when we calculate it, you will notice when we did our calculations here, we had to do our ice tables, and you would know that depending on the Ka, the concentrations of H3O plus is not very high relative to the original acid, okay, like right here. So that's why I can say that, where's my stuff here? Okay, that's why I could say it's a very low concentration. Now, but when we add the conjugate base in the form of a salt, what you have is you have acetate ions as a common ion. So what does that do to the equilibrium? Well, we still have the same equilibrium equation. Okay, so nothing is different here. Oopsie. But the key difference now is you have a high concentration of your acid, a high concentration of your conjugate base salt, and your H3O plus is still low. Now, notice that there is no difference in the products, but the key difference is the concentration. Okay, what I've circled in red. Now, if you take a look at this, the above equilibrium is new to us. CH3COOH is a weak acid, and as such dissociates very little to produce CH3COO-1. With the addition of the conjugate base salt, you have increased the concentration of acetate ions. We now have relatively large concentrations of both the acid and its conjugate base. And the large quantities play a major role in the Le Chatelier shifts, which occur in the buffering process. Now, what I can do is prove this mathematically. Now, when we did our weak acid, weak base calculations, remember Ka was equal to the products over the reactants. Now, but if we were to rearrange this, range here, and just notice we're focusing on H3O plus, we find that H3O plus is equal to the Ka value times the ratio of the acid and its conjugate base ion. And one key thing you should notice, the Ka value here is always constant. Remember, K values are constant. So basically, the H3O plus is dependent upon the ratio of the acid and its conjugate base ion. So this ratio is key, okay? Now, so how does that work? So what I'm going to do is I'm just going to let you take a look at these two. And I think I left a blank space in your notes. You can just copy it down. So you can pause it here while you copy down this information, okay? All right, the pause is stopped, okay? What happens when we add an acid? Okay, so when you add an acid, what happens is, looking at the equilibrium, the small amount of H3O plus combines with the extra acetate ion to form acetic acid. The high concentration of the acid and the base originally, it does not change the ratio of the acid and its conjugate base by a great deal, and the pH of the solution is relatively unchanged. Again, if we look back at this top equation here, the concentration of H3O plus is dependent on the Ka constant and the ratio of the acid and its conjugate base. So if the ratio amount doesn't change very much, then H3O plus stays constant. Okay, same thing with the base. If you add OH minus 1, what happens is the small amount of OH minus 1 reacts with the CH3COO present to produce water. But again, because of the high concentrations of acetic acid and its acetate ion originally, the ratio between the two is not affected by that much. and therefore the pH is relatively unchanged. Okay, so again, it depends on the ratio of the ion and the acid. Example I would give you would probably be something like if you get your hair cut. Now, if you get a haircut and let's say your hair is as short as mine, you take off 1 centimeter, that's a lot of hair for my case. But let's say if somebody else has, shoulder length or, waist length hair, and when they cut their hair 1 centimeter, it doesn't really affect their look very much, okay? And the person with long hair would be like a buffer solution because they have so much hair originally before, so much hair afterwards, the ratio hasn't changed very much. For me, and my hair example would be like pre-buffer. If I took off 1 centimeter of hair, that amount of change would be huge. Now, down here, what it is showing you graphically of what it would look like if you added an acid or a base. So this would be situation number 1, where you add an acid. And here on the right-hand side, you have situation number 2, where you add a base. Now, notice in a buffer system, what's happening is you are either reacting with the conjugate base ion or the acid. Okay, now, buffer systems have their limits. So if large amounts of H3O plus or OH minus 1 is added to a buffer, the system is overwhelmed and the pH changes significantly. Now, I wanted to go back to situation 1, situation 2. Some of you might say, well, Mr. Chan, I don't get it. Could I not do this for a buffer system? So let's say CH3 and H2O in equilibrium gives you CH3, COO minus 1, and H3O plus. Now, for situation number 1, if I increase the equilibrium, doesn't it shift could I say equilibrium shifts to the left? Concentration of CH3COOH goes up. Yeah, notice how I wrote it here is you're producing CH3COOH. Now, some of you might say, well, Mr. Chan, if we had a base, doesn't a base decrease the H3O plus? And so equilibrium shifts to the right and CH3COO concentration goes up? Yeah. Take a look at the products in situation 2. You produce CH3COO2. Now, you might say, okay, which one is correct then? Which way? When we talk about buffer systems, you want to focus on the fact that it's the acid or base are reacting with the conjugate ion or the actual acid itself. And the reason being is because you have a high concentration of the acid and a high concentration of its conjugate base ion. And these, due to reaction kinetics, would react with any extra acid or base that is added to the system or added to the reaction. Okay, it's not saying that looking at it in equilibrium, shifting left or shifting right is not true. All right, doesn't work. But in reality, because of the fact that you have a high concentration of the ion or its acid, those are the ones that react with the extra H3O plus or OH minus ones that's added to the reaction. All right. So that's what I'm going to do. Stop right here. And then what I'm going to do is the next video, I'm going to go through about 2 or 3 examples just to show you how to approach a buffer situation. All right, folks, thank you very much. Have a good day. Bye-bye.